Now, not all atoms are the same size. Some are big and some are small. We can use the periodic table to compare the sizes of different atoms. Why do we care? The farther the valence shell is away from the nucleus, the more weakly the electrons are attracted to the nucleus and the more easily they can be pulled off. And this can be used to explain reactivity trends. We saw that as you go down the alkali metal column, these metals get more and more and more reactive. And that's because their outer shell is easier and easier and easier to pull off because they get larger going down. Now, let's back up a little bit. What do I mean by atomic radius? Well, if you picture the atom as a sphere, and there's the nucleus in the center, the radius would be the distance between the center and the edge. You might say, well, wait a minute now, this is a fuzzy kind of cloud you said before. It doesn't have an edge, so how can you tell what the radius is? Well, that's a good point. What I'm really going to do is try to use this element to form a diatomic molecule. And I can measure the bond length, that is the distance between the nuclei, and take half of that. So I'm going to define it this way. Now there's a lot of different ways to define atomic radius. If you go and look up atomic radius tables out on the web, you're going to find different kinds of atomic radius. The kind that I'm talking about and the kind that the book is talking about is covalent radius. That's what I've just defined for you here. And it's okay, you can use those other kinds of atomic radius that you find, but what you have to do is be consistent. So if you're comparing two atoms and you want to see which one has a bigger radius, use the same definition of radius for them both. You can't look on one table at the radius for one and then at another table for the radius for another one. So that's what atomic radius is. Now, it turns out to be fairly simple to use the periodic table to compare the sizes of atoms. First of all, the more shells you have, the bigger the atom is. So for example, if I'm looking at my alkali metals here, and I'm comparing lithium, sodium, and potassium, lithium is in the second row, it has 2 shells. And sodium is in the third row, it has 3 shells. And potassium is in the fourth row, so it has 4 shells. And it's pretty clear that the potassium is the bigger atom because it has more shells. So as you go down a column, you get bigger atoms. Here's the periodic table. All right, that's fine. As long as I'm comparing atoms in the same column, I can do it now. And do it pretty flawlessly. There aren't any exceptions to this rule. Let's put a box around it. It's worth remembering. What if I'm comparing things that are not in the same column, though? Well, in this case, things get bigger going this way. So if you're going to the left, or if you're going down, things get bigger. In other words, the biggest atoms ought to be here, and then the smallest ones are going to be up here. And I think that's the easiest way to remember both of the trends at once. But let's go back and look at this. Why do they get bigger going that way? Well, suppose I'm trying to compare sodium and magnesium. Both of them have got 3 shells. There's the sodium. Here, let me draw again down here. Here's the magnesium. Now notice I drew the magnesium a little bit smaller. Even though they both have the same number of shells, these shells are crunched in. How come? If you look at the nuclear charge, what's happening here is that you've got a plus 11 charge in the middle of this. If you look at the atomic number, it's 11. So there's a plus 11 charge on the nucleus. And if you look at the charge here, it's plus 12. So there's a larger nuclear charge, and it is drawing in. It is drawing in those shells. It crunches them down. And that's what creates this trend, going bigger to the left. We were going to the left here. Now, these trends are generally correct. So there are going to be some irregularities, just like there were irregularities in the Aufbau principle, in the electron configurations. There are some irregularities in these 2 rules. But generally, if someone throws a list of atoms at you, you can now rank them according to whether they're larger or smaller. Let's try it. Let's suppose somebody gives you, I don't know, francium, I don't know, we'll pick out some weird ones. Rhenium and zinc and sulfur and fluorine. And they say, order them increasing size, according to increasing size. So when someone says increasing size in a question, they want you to put the smallest one first. And the largest one last. Now, I don't know if you're like me. I have a little bit of dyslexia, so I tend to get things backwards, right and left, I confuse. So I see a lot of people confuse when someone says increasing size, they'll put the largest one first and the smallest one last. So if you're one of those people, be especially careful with the wording of questions like this. All right, so how do I do this? I can use my periodic trends here, bigger to the left and bigger down, to do it. Let's look at where these things are on a periodic table. Let's see, I got francium. That's here. So let's draw a little table here. So francium is down here. Rhenium. Actually, that's rhodium. RH. There it is. It's like in there. And then zinc is up there. And sulfur is over there. And then fluorine is up here. Now, the biggest things are down here, and the smallest things are up here. So I'd say in order of increasing size, it's kind of the opposite of what I wrote here. It would be fluorine first, and they'll say it's less than the size of sulfur, which is less than the size of zinc, which is less than the size of rhodium, which is less than the size of francium. So I can kind of draw where they are on the table and kind of order them that way. If someone gave them to me in a different order here, I'd be able to straighten it out and rank them. I'm asking you to do this in the question below this video. Now, there's another case. Here we're comparing atoms, and this works fine for comparing atoms. So this is good for comparing atoms only. What if I'm comparing ions? What do I do then? You can't just do what we just did. That's only for comparing atoms. Well, let's suppose I want to compare a sodium atom with a sodium ion and see which one's bigger. Okay, well, sodium atom has got 3 shells, and it's got a 3s1 is the valence shell. So does 1 electron in its valence shell. If you take that 1 electron off to make a sodium ion, you're stripping off the valence shell. There was only 1 electron in that outer layer. So a sodium ion is only going to have 2 shells. So you can see pretty clearly which one's bigger. The sodium atom is bigger than the sodium ion. So plus ions are smaller than the atom they came from. Now, what happens if you have a negative ion? Like, let's compare chlorine and chloride is what they call this. We're going to learn about naming them in a future lesson. Well, where's chlorine? There it is. It's got 3 shells. Outer shell has how many electrons in it? 1, 2, 3, 4, 5, 6, 7 electrons in the outer shell. Now when it becomes a chloride, it gets an argon configuration. So it has 8 electrons in the outer shell. But it still has 3 shells. Now, there's very little difference in size between these because they both have the same number of shells and they have the same nuclear charge. But there is a slight swelling. Why? Why is that very slightly larger? Well, electrons repel each other, and if you drop an extra electron into the valence shell, they are all going to try and move away from each other. Remember, electrons hate each other. They're all negatively charged. Negative charges repel negative charges. All right. Now, what about isoelectronic series? Those are actually simpler to compare. Let's look at the isoelectronic series that we were dealing with before. We said the isoelectronic series can be built up for neon. It looks like nitrogen wants to pick up 1, 2, 3 to get a neon configuration. Oxygen wants to pick up 1, 2, so that's in the series. And if you don't know what I'm talking about as far as an isoelectronic series, maybe you missed the frame a couple of frames back. Go and watch the video on isoelectronic series again. If you've got a fluorine, it wants to pick up one electron to become neon, a neon configuration. If you look at sodium over here, it can lose an electron to become neon, and magnesium can lose 2 electrons, 1, 2, to become neon. And aluminum can lose 3 electrons. So here's an isoelectronic series. We'll throw neon in there. All of these things have a neon configuration. Now, suppose someone turns around and says, which one's biggest? Which one's smallest? Put them in order of increasing size. Now, they all have the same number of shells because they all have the same configuration. So what's different about them? The nuclear charge. Let's write in the nuclear charge for each of these. Well, nitrogen is got an atomic number of 7. Oxygen is got 8. Fluorine has got 9. Sodium has got 11. Magnesium has got 12. And aluminum has got 13. And neon has got 10. Okay, in an isoelectronic series, since they all have the same number of shells, so you can't use that rule. But you can use the rule that says smaller nuclear charge. It gives you a bigger atom. This is the same rule that makes things get bigger as you go to the left. You have a smaller nuclear charge as you're going to the left on the periodic table, and that gives you a bigger atom. But here we're not looking at the periodic table anymore, except to get the nuclear charges. Which one has the smallest nuclear charge? This one. So this one's going to be the biggest. What's the next? Okay, so we take that one off the list. What's the smallest nuclear charge out of what's left? This one. Let's take that out of the list. What is the smallest nuclear charge out of what's left? Okay. Let's look at what's left. What is the smallest nuclear charge out of what's left? The neon. Okay, take that out. What is the smallest nuclear charge out of what's left? Now we only have these two. What is the smallest nuclear charge out of those? And then, so I put those all in order in the isoelectronic series, from biggest to smallest in this case. So if they would have asked me decreasing order, I would have had it right. If the question had asked me increasing order, I need to do that backwards, right? I want to put the smallest one first, and the biggest one last. That would be increasing order. So it was a little heartbreaking to know what you're doing, and then because of like a little bit of confusion about direction, a little bit of dyslexia, get it wrong. So be especially careful about what the question is asking, which one of these two possibilities you choose. So now you can compare the sizes of isoelectronic series as well as the sizes of just atoms and the sizes of ions with the atoms that they came from.